Hello, everyone, and welcome back. Thanks for joining us again. I am pleased to introduce Igor Markov, research scientist at Facebook. Igor, welcome to the stage. The show is yours.
Thank you for the introduction. It's good to be back at MLconf, and I have to appreciate the sequencing of presentations. The previous talk introduced a number of concepts and notions that I will need, so I will not need to repeat them. This talk covers material that we just recently posted on the archive, and it's a large paper with 20 authors. This was a team effort over multiple years. The work is deployed, and in fact, you've been probably using it in some ways. Now, before I start, the picture on the left shows me at the New York Stock Exchange. This was a cool visit. A friend's company did an IPO, so they invited several people. And this was early in the morning, 9 o'clock, 6 o'clock Pacific time, but very exciting. Okay, the abstract here is a copy of the archive abstract. I'm not expecting you to read all of this now, but the agenda roughly follows the structure of the paper. So many of the details are covered in the paper, of course. I will discuss horizontal versus vertical ML platforms, and we are dealing with declarative AI as described in the previous presentation. I will introduce the notion of smart strategies and discuss what it takes to implement them in modern software. I will, of course, summarize our contributions and then revisit them at the end of the talk. The core of the material is the Looper platform. I will discuss the general concepts that went into the platform, the philosophy, the architecture, a specific abstraction that we call the strategy blueprint, the platform specializations, and in particular, one very important specialization called a personalized experiments, which uses A/B testing to tune ML models to product impact, to improve product impact. I will cover the impact of smart strategies. This will include 2 application deep dives. This will include a discussion of adoption and the impact within Facebook, and some data on resource utilization, showing where the bottlenecks are. To better understand the adoption, we did a survey of adopters of our platform inside Facebook, and I will outline the learning curve and how long it takes to adopt the platform to launch products on it. Now, the idea behind the use of ML, in our case, is to implement so-called smart strategies that make decisions for software systems. We work with existing software that may or may not have anything to do with ML, but we find these decision points that basically require some behavior, some policy, and the default policies are typically not the best. For example, in products interacting with many users or the environment, we need to learn from the users, we need to learn from the environment, and closed-form policies are not only far from optimal, but policies need to change with data. So you have to learn from data and ideally personalized policies to users. Here are some examples. This is list is by far not exhaustive, but you can think of application settings and preferences. There are some defaults, and some users may want to change them. When do you even ask the users about changing the defaults? Now, the interfaces for mobile devices are very screen limited, and adaptive interfaces can show some options only to users who are likely to be interested. And this needs a prediction. This needs some ML model that tells you when a user is interested or might be interested. This approach can control the frequency of ads, user notifications, and really anything of that nature in your application. Now, the next item, prefetching or precomputation to reduce latency, is not targeting the users as much as it targets systems. Basically, any download to a mobile device or any complicated file transfer or anything that uses resources could benefit from prefetching, but it's a trade-off between bandwidth and latency. So predicting what to prefetch and what not is a pretty important line item for many companies. Another item here in examples is content ranking and prioritizing available actions. You could imagine a menu with many items, and showing 20 menu items is just not reasonable. You have to prioritize them, right? And then content ranking can be illustrated by, say, newsfeed. Now, the next slide is pretty crammed. This is straight from the paper, but let me emphasize what's really important here. So the systems that implement these smart strategies, the platforms that implement them, can be subdivided into specialized and general purpose. You have the left and the right column, and also vertical versus horizontal. So the horizontal systems are shown in the middle. Think of PyTorch or TensorFlow. These are mostly toolboxes that offer capabilities, but how you use them and how you connect them to the products, that's really up to the vertical systems. And for specialized vertical platforms, there are a number of publications discussing how Netflix uses ML, how YouTube uses ML, for Facebook, of course, too. Things like video processing, audio processing. This usually requires specialized platforms because of large data sizes. But general purpose vertical platforms operate on lightweight models, or they use lightweight models to operate on more modest amounts of data. And these data typically come from different sources. So you don't have time and engineering capacity to optimize to build a system for each use. You want a platform that can host multiple such smart strategies. And you also get an economy of scale through reuse. There are many features that are listed here that can be used over multiple models. Okay, so general purpose models have a large variety of use cases, and the task is really for us to go all the way vertically from data sources to product impact. Now, most systems don't go all the way down. They deploy the model, they can maintain the model, and the previous talk did a pretty good job covering many of these issues. In this work, we go further. We use Facebook's infrastructure for measuring things, and we connect the models to the measurement infrastructure. We also use A/B testing to optimize the ML models and, in fact, the entire stack for product impact. And we do things like daily retraining. Many of these things are automated. So I'll cover that in more detail. Now, the contributions in this work are mostly under a vertical end-to-end platform called Looper. It is an internal platform at Facebook that targets product engineers, potentially without ML background. The ease of use is one of the major concerns, and the rapid deployment of models. And they'll give you data on how long it takes to deploy models on our platform. Data sizes are moderate, although, of course, it's just a matter of infrastructure. We could definitely scale things up. Model complexity is limited mostly because our models tend to be retrained very often. And again, we could go higher, but this has not been a concern. In fact, it turns out that in many applications, model complexity is not a bottleneck. Just like in the previous talk, we are talking about declarative AI, so no ML coding or expertise required. You may need to write some code, but it's not ML code, right? And in this notion of end-to-end, we go from data collection, and we collect data online through an API instead of saving data into some files and then doing something with them. And we also optimize product impact. This is going from data collection to optimizing product impact via causal experiments, meaning A/B testing. And this is a very important part of the system that drives a lot of adoption. Among the technical highlights, I can mention strategy blueprints and abstraction layer. Our system is API driven, and it is tightly integrated with AutoML. So we can tune the models, we can tune hyperparameters, we can tune data sources. And this tuning is done based on personalized experiments. Okay. Now, to review some of the background that goes into deploying ML for smart strategies, of course, you have to approximate product goals with some predictable outcomes. Meaning, a closed form objective function may not quite be a good match for any particular application, but there are many ways to course, product goals into ML objective functions. Once you have some ML deployed, you need to process the numbers that come out of it into decisions, and that is done by decision policies, right? When you have the flow configured, it turns out you have a choice of ML models. And for example, we find that GBDTs often are more appropriate than deep learning because they're faster to train, they consume fewer resources, and they're good enough. Another aspect of ML for smart strategies is the use of metadata features. This is different from many publications in ML that you find at NeurIPS. Because we are not processing images, we are not processing multimedia. We typically process metadata, clicks, file sizes, some account parameters, and these come from different sources. They're not on the same scale. They can be categorical features, integer features, Boolean features, floating point features, and they pose a number of interesting concerns. And I'll mention even how they affect the bottlenecks. Now, in any significant system, you need to perform logging and monitoring of ML performance. Sometimes things, go sideways. And we also pay attention to optimizing resource usage. In fact, this is one of the big selling points for the platform. We can optimize your models without you knowing how to do that. Now, on the right, there's a figure from our paper. It shows various ML tasks and models that we can deploy. You can see that binary classification is a large fraction of applications, but we also have regression for prediction. We have contextual bandit for cases when the feedback we get has a lot of noise. We have multitask models, and we have some use cases for reinforcement learning. And you can find that in some of our past publications. For model type, you see that we use GBDTs a lot. We use also sparse NN, and we have some models for PyTorch Mobile. This is increasing in use, and we have, of course, reinforcement learning deployed. Okay, now moving into the general principles behind our platform. First of all, it's very important to understand the scope of the work. As I mentioned, we work with metadata. This is a mix of categorical, sparse, and dense features. This affects the choice of models. This affects how you process the features. And the models are lightweight, deployed quickly in large numbers. We have hundreds of models deployed and running on the platform. Data trends may change quickly. This calls for regular retraining, and this is done automatically with automatic deployment. This requires canary, meaning shadow deployment. You see how a good model works compared to a deployed model, and promote it if everything is good. Now, our platform is intended for company engineers. This means that we optimize fast onboarding. We optimize robust deployment. We don't want our users or our adopters to make mistakes. We intercept mistakes. The interface is very simple, and we don't want them to spend a lot of time maintaining their applications. We want them to create more applications. Now, the last bullet is really, really important because the impact of deployment is measured and optimized directly in application terms. You may have some nice objective function with L2 loss and some weight in your ML model, but how does that translate to product impact measured in your application? So we take care of that, and we optimize whatever you parameterize for product impact. Okay. Now, another aspect of the system, and now transitioning to the architecture, is its software-centric integration of ML. I have to be careful here because the data-centric integration is a fairly new trend, and it's promoted by Andrew Ng and a number of people. The point they're making is that instead of thinking of models as software, you just use models as black boxes, and you need to think of data. You need to pre-process data, pay a lot of attention to data. We don't argue with that, but we find that in our case at Facebook, we do have a lot of data of reasonable quality. And the bottleneck for deployment is really the application software. So the way we deploy Looper, or the way we deploy models on Looper, to applications, we use API calls, and we embed API calls straight into software to intercept decision points. Okay, and these API calls can collect data for you before you train your models. This allows to support a dataset abstraction that delegates data quality issues to the platform. And it's easier to reason about training because you don't have to look into all these data issues at this point. Now, these APIs support an online-first approach where we don't, save data into files. First of all, we first get them from API calls, and then the platform manages them. Okay, so we log the features and the labels. For example, if you're working with prefetching, a little bit after the decision was made, you would know whether this decision was reasonably good because you know if the data was needed or used. And so we can collect labels this way, and then we join them in real time. So before you have a model, you just collect features and delayed labels. And when you have the model trained, you can log the decisions and then the labels after that to evaluate the decisions. Now, collecting this in real time and online avoids data leakage and all sorts of discrepancies that are a problem if you kind of collect data at a low level without abstractions. And we refer in our paper to prior work that points out how this really improves data hygiene. Okay, the core of our platform architecture is shown in this diagram. And in the paper, there's a step-by-step description how this works. It starts by registering the API. So the application registers through the API a model on our platform. And then you get the application context, which has links or IDs to various features. After this, you need to get a decision ID, which helps to look up a model if you already have a trained model. Now, based on the application context and decision ID, you can look up a blueprint which has a lot of versioning info and really allows you to reconstruct the entire process from data to decisions. Using that, you look up the data in Feature Store, which is a data warehouse within the company. And then the fun starts. You have the predictor that after joining all the features into one row can perform predictions. And these things get logged. As I mentioned before, they're joined, all the features, predictions, and whatever labels you get. There's a monitoring system. There are training tables. You can train a model based on these data. When the model is trained, you deploy it in a shadow mode. That's called canarying. You measure its performance, and if it looks good, you promote it to production. This has to go through the config system, and the blueprints have all the versions of the models, and they track data compatibility. So this supports a lot of the high-level operations on the platform. Now, the strategy blueprint has a number of components, in this case 4. It's feature configuration, label configuration, model configuration, and policy configuration. And it captures compatibility between models and data, between different data sources. And it supports vertical optimizations where you can choose different things. You could work with different versions. You can backtrack if something didn't work, and you can perform A/B testing with multiple online experiments. This is an illustration of the strategy blueprint. I'll just go over the left side. Basically, you start by tracking everything in blueprints. There are multiple blueprints in the experimentation system. The blueprints allow the API to instantiate the model and all the data sources, all the decision policies, and then the adaptive experimentation system can perform rounds of experiments. Right? It will collect training table, and I'll mention a bit later that we track personalization. We can create a personalized model that can predict who will benefit from a particular treatment, and we're trying to make sure that users don't get a treatment because it benefits a lot of other users. They get treatment because it's likely to improve the experience for these users. Okay, so lots of details here that you could find in the paper. And this platform architecture supports a number of specializations. There are several layers, the core and then specializations. One is Looper for ranking. This is conceptually straightforward. We support various ranking objectives. There's the notion of positional bias that we also support. There are detailed APIs where you can get a ranking as a prediction. And a different specialization that I wanted to cover here is integrated experiment optimizations. Right, this is the use of A/B testing, not to just evaluate the products, but also to optimize them or optimize the model for product metrics. An important notion here is heterogeneous treatment effects, where we can automatically build a model that predicts which users benefit from a particular treatment, right? So this could be, for example, showing something on the screen that you might be interested in. And for users who are not likely to to use a particular feature in the Facebook app, we will not show that. We will save the screen space, right? So this supports automatic personalization, right? And the really serious complication is that this needs to be supported in A/B testing. Even if you do one round of A/B testing, it needs to support personalization. And this is difficult. There's a lot of statistics that goes into this. Now, once we have that working, we can do optimization of product impact, for example, by hyperparameter tuning using Bayesian optimization. Bayesian optimization, and we have some packages developed at Facebook that are open sourced. What they do, they minimize the number of queries, the number of experiments that you have to perform to optimize parameters, because we don't want to try 20, 30 times if we can decide something in just 3 experiments. Okay, and these experiments are pretty difficult. They take time, they take resources. Okay, now I'm transitioning from the platform architecture to applications and impact. So I'll cover 2 application deep dives. One is for data prefetching and one is for personalized experiments. Data prefetching is used in many systems at Facebook, and it is often integrated deeply into the software stack for products and infrastructure. One example is Facebook's GraphQL decides which prefetch techniques to service. Essentially, if a part of the software stack requires some resource from a different part, whether we want to make that resource available early and essentially speculatively use bandwidth, or we want to wait, right? So this can save clients bandwidth, but also there is impact on latency. Okay. It turns out that this helps, especially at the peak server load. It gives 2% compute savings, and at Facebook scale, that's quite a lot. Also, things are already quite optimized, right? A different example is predictive screen rendering by Facebook's app client on smartphones that are older or simpler, and the resources there are limited. Again, we predict what the user might want to see, and so if they actually want to see it, it will be ready, right? But if the user doesn't want to see that, then we wasted some time. Okay, and one insight that came out of these techniques is that user embeddings based on user history are very helpful as features for the models. Okay. A different application here is personalized experiments. I described them before. Let me get into, greater depth on this. So I mentioned the heterogeneous treatment effects, and experimentation is kind of based on that, right? So they're supported, and also they can improve the benefits of smart strategies. Now, from the application perspective, for engineers, product engineers who use this capability of our platform, there is a simpler learning curve than doing this without our platform. For some products, people do this kind of by hand, step by step, but we automate a large part of this work. And this is done by embedding Decision API in client code. In this case, client means other Facebook software. And we have a standard A/B testing API. Okay. The data set preparation is automated, and if you don't have that automation, that's a lot of work. And then, of course, the modeling flow, where we build an ML model that predicts which users will benefit from this treatment, that's also a lot of automation. Now, comparing the impact of smart strategies to baselines, again, requires experiments and automation, and that is done in our platform. What we gain here by integration with Facebook infrastructure is a significant amount of metrics that are maintained by Facebook for various applications. And so there are online, offline metrics that are delayed, such as daily active people, users, and we optimize the models using multi-objective optimization. Okay. Now, application or adoption and impact of our work. The platform is used by over 70 product teams at Facebook. The number of models deployed is growing, but last time I checked, it was over 660. There are about 5 million predictions per second over these models. And there are 5 application categories in the decreasing order of utilization, both the number of models and the resources. So personalized experience and experimentation are very popular among product engineers. There is ranking, of course, for various applications, data prefetching, user notifications and prompts. This is where you are likely to benefit from this directly as a Facebook user. And then there are value estimation applications where we predict, for example, the latency or memory usage of a data query. Here's a summary of impact on resource utilization. So figure 5 on the right from our paper shows that the light blue column is a bottleneck in many cases, and it's feature extraction, right? So it may be surprising that feature extraction is the bottleneck. It's not inference itself. It's not training, although sometimes they take significant amounts of time. In part, this is because we select lightweight models, such as GBDTs, and we use a lot of metadata, which requires joining from different sources. This is different from, for example, deep learning for image processing or audio, right? But that's where the bottleneck is, and that's probably true for any smart strategies, not only at Facebook. Okay, now we did a survey of users, or by users I mean adopters inside Facebook of our platform, and it's hard to ask them, what prevented you from using our platform, because these people, we don't even know who they are in many cases. But fortunately, these reasons for ML strategies to fail are summarized in a recent paper. So we wanted to know what helps people succeed. And it turns out that our platform helps address a number of challenges that people run into, engineers run into. And these are listed here, such as manual optimizing parameters in large search spaces, figuring out the correct rules to make heuristics effective, meaning they had some heuristics deployed, and changing these heuristics is just a nightmare. They become complicated, hard to maintain, especially if some people move to a different group. But ML models tend to be easier, and they provide results that are practically as good or sometimes better. Trading off multiple objectives can be difficult. We automate that. And then updating heuristic logic quickly is a challenge, especially for mobile device code where the release cycle is very slow. But ML models can be retrained on a regular schedule. Okay. It turns out that of the teams using our platform, only 15% had any ML expertise in those teams. And this is why easy to use ML platform is a deciding factor for adoption. Otherwise, these product teams simply cannot afford deploying a model. And we mentioned in the paper a lot more details from the survey, but there were many specific things that engineers tried to do, and they just ran into complications with infrastructure, but our platform allowed them to do this. Now, even for experienced engineers, automation is a big selling point. Maybe they know how to do something, but it just takes a lot of time. And also abstracting all sorts of model versions and package versions into the platform helps people not worry about low-level details. Now, here is the adoption curve, and this is averaged over several, dozens of applications. It takes 2 days to configure a model on our platform. Training the model on product feedback and revising it takes 1 to 2 more weeks. Online product experimentation takes longer because we have to wait for the users to actually experience the smart strategy, and then we collect the behavioral data. Product launch often happens within 1 to 2 months after the initial data collection. This is pretty fast. And as I mentioned, we have hundreds of models deployed. Here are more things that engineers mentioned as benefits of our system. I'll skip them because time is running short. But in conclusion, let me just summarize that we discussed smart strategies that enrich modern software, and they learn from data. They don't use any closed form policies. They adapt, and they also personalize the software to users. These strategies are supported by a vertical ML platform that is accessible to product engineers without ML expertise. And it's evaluated by product impact, which is a nice step up from many of the previous works and much of the industry practice. We extend the notion of end-to-end platforms to include online-first data collection to intercept decision points in application software using platform API calls. We support user personalization, and we can optimize product impact via A/B testing. And of course, this has been used at Facebook for some time now. The details are in the archive paper, and of course, the team is large. You can see who worked on this team by looking at the authors of the paper. At this point, I'm going to take questions, and I'll keep the archive ID on the screen.
Thank you, Igor. Terrific session. If you have any questions for Igor, please enter them in our chat, and we'll keep monitoring what comes through. And Igor, even when you are concluded, if you could just stay in the audience and view the chat on the stage. Sometimes folks put things in even though you've concluded. I don't see anything coming through just yet. Give it another second here.
I'll be around.
Okay, great. Great. So if you folks out there in the audience have any thoughts or questions, please continue to enter them in the chat. Igor, we thank you for sharing your presentation and this great information. And I am going to close this broadcast, and we're going to bring Sheng Jia into the backstage, and I'll be back with you all in 3 minutes. Thank you, Igor. Many thanks.